In this video, I'm going to focus on a specific strategy for solving part-whole problems. We're going to discuss counting on, and we're going to look at how this progresses as we progress through school. Of course, this strategy can be used when solving different problem types, but for now, we'll concentrate on part-whole problems. There are two possible scenarios for these types of problems. Either we don't know the whole amount, or we don't know one of the parts. In this first video, we'll focus on problems where we don't know the whole amount. We can see from this visual representation that to find the whole amount, we need to add those two parts together. Let's consider a typical problem. Mark had 8 sweets. His mum gave him 5 more sweets. How many sweets does he have now? This is an obvious addition problem because he is getting more sweets, so the amount of sweets is increasing. Let's consider another problem. Mark had some sweets. He ate 8 of those sweets and has 5 left. How many sweets did he start with? In this problem, some of the sweets are being eaten, so the amount of sweets is reducing. For this reason, it's a common mistake for pupils to solve this using subtraction and get an incorrect answer of 3. When we represent the relationship between the values visually using a bar model, we can see that in this occasion, the amount of sweets that he started with is the whole amount, so it's the whole amount that is unknown. Exactly the same relationship as the previous question. Maths isn't just about numbers and abstract calculations, it's about being able to analyse and identify relationships and make decisions based on this understanding. It's really important that maths problems are set within a context. This allows pupils to make sense of the relationships and values and develops their reasoning skills and a deeper understanding of maths. Now that we've analysed these problems and understand the relationship, let's consider how we might solve them. I'm going to use resources to do this, so I've got tens, frames and counters. Let's start by putting out 8 and then 5. I'm also going to use an open number line to record my steps. Let's start with one of the parts. We could start with 5 and count on the 8 because addition is commutative, but I'm going to start with 8 and count on the 5 because this involves less work. As we progress with these strategies, we become more efficient. To begin with, I might count on 1 at a time. So from 8, we can count on 9, 10, 11, 12, 13. So our answer is 13 sweets. In this example, we counted on in ones. This is fine for the small numbers that are involved in this example, but what if we want to move on to larger values? We need to find a more efficient strategy. Let's have a look at how we might solve this problem in a more efficient way. Let's start with the 8 again, only this time let's not count on 1 at a time. The tens frames are an excellent resource for developing efficiency because I can see that counting on 2 would get us to 10. So let's count on 2 and record this jump on the number line. Now that we're at 10, a friendly number, it's easy to count on the 3 to get to 13. We've solved this using 2 steps or jumps instead of 5 that we did before. We're becoming more efficient because we're using jumps to bridge to a friendly number. And as we become more confident, we can apply this understanding to larger values. Let's not rush this though. Focus on developing that confidence with the strategy and gradually increase the values. Let's have a look at a problem with larger values. Mark had 38 stickers. His mum gave him 25 more stickers. How many stickers does he have now? Let's analyse this problem using a bar again. On this occasion, the whole amount is the number of stickers he ends up with, and there are 2 parts. The number of stickers he started with and the number that he received. When we put in the known values, we can see that we've got a whole unknown problem once again. Let's use those tens, frames and counters again to make the numbers, and again we'll record our steps on a number line. I'm going to start at 38 and count on the 25 because I think that's less work than doing it the other way around. There is no set way to do this. I'm going to start by counting on 2 to get to 40. Then I'm going to count on the tens 1 at a time to get to 60. And finally, I can count on the remaining 3 to get to 63. I could just have easily started by adding on the tens. 1 10 to get to 48, then the other to get to 58, then adding that remaining 5 in 2 steps. 2 to get to 60, a friendly number again, then the remaining 3 to get to 63 once again. Or I could have done that in fewer steps. Let's start at 38 again and count on 2 to get to 40. Now that I'm at that friendly number, it becomes much easy to add on that remaining 23. So rather than breaking that down and doing it in more jumps, I can add on 23 in one jump. Using tens, frames and counters like this really develops this efficiency, and it reinforces our understanding of place value, something that a traditional algorithm fails to do. You'll notice that for each example I'm using concrete resources or pictorial representations of them, while at the same time I'm recording my steps in a number line. The number line is not an alternative strategy, but merely a more abstract and efficient means of recording our steps. The ability to visualise our steps using the resources and number line in this way develops our ability to perform these calculations in our head. However, it is vital that we continue to encourage pupils to make their thinking visible throughout their school life, as this allows them to articulate their thoughts, increase efficiency, and make connections between strategies and mathematical concepts. It allows us as teachers to see the pupil's thought process, allowing us to more accurately assess understanding and identify misconceptions. It's far more important that we're able to reason with a problem, articulate our thought process, make mistakes, learn from those mistakes, and apply our understanding to new contexts than simply getting the right answer. Let's have a look at an example using much larger values. A plane is flying from Glasgow to New York. So far it's travelled 1,586 miles. It still has 1,635 miles to go. What's the distance from Glasgow to New York? Once again, let's analyse using a bar model. The whole amount is the total distance from Glasgow to New York, and we've got two parts: the distance travelled so far and the distance still to go. We know it's travelled 1,586 miles so far, and it still has 1,635 miles to go. So again, we're looking for the whole amount in this example. This relationship remains consistent throughout all of these examples, whether we're working in single-digit problems or four-digit problems like this one. Because we're dealing with such large values, I'm going to progress on to using Dean's materials to represent them. It's important that pupils have a deep understanding of making 10, which we've developed using those tens, frames and counters, before we progress on to the Dean's resources. Once again, I'm going to count on using the materials, and I'm going to record my steps on the number line. Let's start at 1,586 and count on the 1,635. I'm actually starting with the smaller number this time because I've got less of a jump to get to the nearest 100. I'm going to start by counting on 14 to get to 1,600. Then I can count on 400 to get to 2,000. I've only got 1,221 left to count on. Because I've got to a much friendlier number, that 2,000, I could actually just do this in one jump. But let's just count on the 1,000 and then the 221 to get to 3,221. So the total distance between Glasgow and New York is 3,221 miles. Of course, there are lots of different ways that we could have done that. It's not about doing it in the same way as me, it's about doing it in the way that makes most sense to you. The final problem we're going to look at applies this strategy in a context involving decimal numbers. Money is perhaps the easiest context to develop and apply this understanding. Paul went into a shop and bought a t-shirt for £14.89. He left with £7.43 in his wallet. How much money did he go into the shop with? Let's analyse. The whole amount is the amount of money he started with because that's all the money that he had. And we have two parts because he spent some of his money in the t-shirt and he left with some money. We know the t-shirt cost £14.89 and he left with £7.43. So once again, we've got a part whole question where we don't know the whole amount. You may wish to use place value counters for this one, or as I'm doing, actual money. Place value counters are a progression on from Dean's. When we use Dean's, the scale of each value is represented by the physical resource. A 10 is physically 10 times bigger than a 1, 100 is 10 times bigger than a 10, etc. Place value counters are all the same size. Because of this, they're more efficient to use, but it's important to understand the scale of each place before making this jump. I'm going to start with £14.89 and count on the £7.43. I can start by counting on 11 pence to get to £15. Now that I'm at a friendly number, I might want to add on £5 to get to £20, which is an even friendlier number. And then finally, I've got the remaining £2.32 to get to £22.32. So he went into the shop with £22.32. As you can see, not only has the relationship remained consistent regardless of the level we're working at, but the strategy of counting on has also remained consistent. Yes, we've become more efficient, applied the strategy to larger values and a wider range of contexts. We've introduced decimals and made use of different resources to suit our learning needs, but the basic strategy has remained unchanged. This consistency applies across curricular organisers, so we don't need to think about teaching money, measurement or time in isolation. These can be used as a context through which we can develop an understanding of mathematical relationships and strategies. Join me in the next video where I'll be solving part unknown problems using exactly the same strategy of counting on.